So what we're doing now is we're going to talk about nuclear energy. Nuclear energy is a little more complicated than the other forms of energy, and it's dealing with terribly tiny values of energy. I mean, we think of a nuclear bomb as being this massive amount of energy being released. But what is really going on an atomic scale is that there's very little energy being released per atom, or per molecule, well, per atom, not per molecule, per atom. So you have to have a tremendous amount of atoms in one given space. Well, we know from Avogadro's number that it's not all that difficult to get a tremendous amount of atoms into a single volume. So, you know, massive bulks of atoms releasing small amounts of energy very quickly gives us the nuclear explosion that we're used to seeing. But what we're going to talk about when we talk about nuclear energy, we need to come up with some new vocabulary. The first one we're going to come up with is the atomic mass unit, the unified atomic mass unit. The mass of a proton and the mass of a neutron are terribly small. Obviously, I'm not even mentioning the electron because it doesn't even really fit into the equation. We don't talk about the electron being of all importance. So what we're going to do is we're going to come up with this fundamental unit for a unit of mass. And what we're going to do is we're going to use isotopes. We're going to use carbon-12. So we're going to use carbon-12, and we're going to break that up into 12 units. So we say, well, you know, it's a fairly common isotope. We'll take that carbon-12, we'll divide it up and say that there's 12 atomic mass units in that isotope. Okay, so that gives me a breakdown of one atomic unit is equal to 1.66054 times 10 to the negative 27 kilograms per atomic mass unit. Now, terribly small. Terribly small. And then you can see why we want to play with that instead of with that. Okay, well, the breakdown per proton per neutron is listed right here. They're not exactly 1 unit per, they're a little bit more than 1 unit per. Okay, and that has to do with some binding energies that are associated with it. Okay, so an atomic mass unit is a really small thing. Okay, the other thing is we're going to talk about notation. We are going to talk about the notation that we typically use in nuclear physics. So what we got here is, let's say we got this xenon or whatever, xenon being an E there. So it's some sort of atom, and we're going to refer to that atom as the general form is X. If it's carbon, it's C. If it's plutonium, it's Pu. No, it's not Pu. Plutonium. Maybe it is Pu. Yeah, I think it is Pu. Pb is copper, or no, lead. So Pu being plutonium. So we put in the universally recognized symbol for that. I guess it shouldn't say universally, but universally symbol to recognize that element, that atom. And then we have a couple other things. We have the mass number. Well, the mass number is referring to the total amount of particles, neutrons and protons, that are making up the nucleus. Now, the mass number is allowed to fluctuate. If it's an isotope, that mass number may be higher than what it normally is. So this mass number could change if the number of neutrons is higher in that atom. If that atom has a higher number of neutrons than is typical in there, then that mass number is going to be bigger. The atomic number, we should know, is the number of protons. The atomic number is the property. It gives all the characteristics of that atom is based on the protons that are being bonded there. So this mass number is composed of both the number of neutrons and the number of protons. So when we talk about this mass number, this A, we're saying that mass number is equal to the number of neutrons plus the atomic number, which is the number of protons. So neutrons can fluctuate. Neutrons don't really give a lot of property value to that atom. I mean, it does in the fact that it makes it an isotope and can make it radioactive, but it doesn't say that you're going to attract so many electrons. It doesn't say that your probability cloud is going to look like this. It doesn't give me any of that sort of stuff. It's to the electronegative or electric neutral. It doesn't have a charge associated with it. So the number of neutrons is allowed to change, but the number of protons is going to remain constant. As a matter of fact, if you add a proton, which we can do using nuclear physics, if you add a proton, you're no longer talking about the same atom. You're moving along in the periodic table. Okay, so when we talk about atoms, when we talk about nuclear physics, we're using two numbers to talk about. We're talking about the mass number, which is a numerical value, 12, 14. It's a whole integer. That integer is referring to the number of neutrons and the number of protons that are there. Okay, and then we're talking about the atomic number. The atomic number being the number of protons. Okay, so that is a really important piece of information, and you're going to see that over and over again. And then the other thing that we need to talk about is mega electron volts. A mega electron volt is going to be our base unit for energy. We shift away from kilograms, so we want to shift away from a joule. A joule is a tremendous amount of energy if you really think about it. Amount of energy that's required to lift an object that has a weight of 1 Newton, 1 meter. That's a lot of energy, especially when you talk about it on the atomic scale. So we're going to shift to these mega electron volts. Okay, which it turns out it's 1 atomic mass unit times the speed of light squared. That's one mega electron volt, which is really a nice unit to deal with. Okay, so here we go. That's our little symbol to deal with our atoms. We're coming up with a new unit called a unified atomic unit, and then we're going to have to deal with new energies. Okay, so that's the introduction to nuclear